seminar. To start with, please don't talk to each other. Talk to me only. I don't like to be talking while you are talking. In the meantime, you are allowed to ask any question at any time. Don't wait until we finish and then ask your questions. Ask the question when you feel that you want to ask. ماشي؟ يبقى الكلام مع بعض ده. واسألني متى شئت. No problem. نبدأ إن شاء الله. Are we witnessing the third revolution in electronic devices? I don't think that there is anybody now who doesn't appreciate the importance of electronics in our life. Maybe you don't like 203 and 303, maybe. But this doesn't mean that electronics is very essential in our life. Every day, wherever you go, whether at home, in the streets, in the university, electronics is around us. So we must understand the world that we are living in. And we cannot understand it without understanding electronics. So hopefully, you will change your mind after listening to this seminar and see the world in a different way. But of course, the main issue here is not whether you like electronics or not, but the main issue here is history of electronics and how it was, how it changed our life. So, in fact, we have seen two revolutions so far in electronics. The first revolution was the invention of the vacuum tubes. And just probably most of you don't know anything about vacuum tubes. This is a vacuum tube. This is a vacuum tube. It has so many legs to be fixed in a base, and as you see, a glass bulb, and inside it there are electrodes, and there is a filament. When we used, this was 40 years or 50 years ago, to heat the filament first, so this will emit electrons. Once the electrons are emitted, we can attract them by applying a voltage to what we call a node, and we can control their movement by applying another voltage to what we call a grid, شبكة يعني. So this was a vacuum tube. It was invented firstly in 1883, when they noticed for the first time that electrons can move between two metals if they are enclosed in a vacuum. But then the real invention came in 1906, when the first diode was invented. And of course, I hope that by now you appreciate what does it mean diode for us in electronics. Without diode, we cannot have rectifiers. Without rectifiers, we cannot have DC from the AC. Without diodes, we cannot have detectors. And without detectors, we cannot have radio receiver or TV receivers or whatever it is. So diodes was a very important step in developing the electronics which we know today. Next to that, in 1906, the triode was invented. And the triode is the equivalent of what we call now the transistor. It is a three-terminal device with cathode, which is equivalent to the source or the emitter, and with a grid, which is equivalent to what we call today the base, and with a collector, which is equivalent to what we call, with a node, which is equivalent to what we call today collector. So it is a three-terminal device, and its invention made a revolution in the electronic itself, because with this triode, they managed to have an amplifier for the first time. And I hope that you appreciate what an amplifier means for communications. And it is immediately after the invention of the diode and the triode that the communication started to take its shape, and the communication between Europe and the USA been established with Marconi and so on. So the invention of the vacuum tube, followed by the diode, followed by the triode, this was the first revolution for electronics. And we lived with it for so many years, until in the 40s, exactly in 1947, the bipolar junction transistor was invented. And I hope that you know the bipolar junction transistor. It is a triode, but with another structure, of course. It is not vacuum tube anymore, nothing to be heated. So it was all built around silicon. And it was, of course, very small in size. Just to show you, and I'm sure you know, but just for compilation, this is a possible transistor. One transistor only. One transistor only. All of you who have taken 2 or 3 or 3 or 3 are aware about this. This is a transistor. As you can see, the size is much less. No heating, no bends, no too many bends, just 3. One for the collector, and one for the base, and one for the emitter. And it was another very great revolution, which resulted in so many applications. We will see some of them, if possible. Like this was a transistor which was invented in 1947. First, the bipolar transistor, the bipolar junction transistor was invented, and then it took another, and of course, immediately after 5 or 6 years, the idea of integrating so many transistors on one chip came to be in the mid-50s or something like that, and the integrated circuit started to come. And this was the second revolution in the electronics. And this was followed by the invention of the MOSFET. So the MOSFET came a little bit later, about 13 years or so after the bipolar junction transistor. The MOSFET has, of course, it stands for metal oxide field effect transistor. It has a different structure. It happens to be smaller in size, but of course it has advantages and disadvantages. Compared to the bipolar junction transistor, it is very well known for everybody working in electronics that the bipolar junction transistor can provide us with a higher gain, higher than what the MOSFET can provide us. And the MOSFET, the bipolar transistor also is less noisy. It doesn't produce noise by itself. Of course, every passive, every resistance or active element produce noise. The capacitors by themselves, they don't produce noise. But the internal resistance of the capacitor produce noise. The inductor by itself, it doesn't produce noise, but the internal resistance of the inductor produce noise. The resistor, of course, is a great noise producer. The active elements are great noise producers. So the bipolar junction transistor is much better in terms of noise performance than the MOSFET. The bipolar junction transistor is much faster. No, don't drink or eat while I'm talking. The door is open, you can do anything else, and then come back. The bipolar junction transistor is also much faster than the MOSFET, so it can work at much higher frequencies. But the MOSFET has other greater advantage. It can be scaled down. And this is most of the story we are going to tell today is about this scaling down. So the MOSFET can be scaled down, and as such it can be of a much smaller size. And if this is the case, it can be integrated on one chip, and we can get what we know today of the microprocessors, microcontrollers, computers, and the iPads, and all these things wouldn't be possible without scaling down the dimensions of the transistors. Just to give you an idea about the integrated circuits, this is a digital to analog converter integrated circuit. It may contain few billions of transistors inside. Integrated circuits, not necessarily this one, but integrated circuits now of such a size can contain few billions of transistors inside. This is, of course, unimaginable. Using the vacuum tubes, this is impossible. And using even bipolar transistor, it is impossible. And using MOSFET without scaling, it is also impossible. You agree with me? So let us go through this slide fast. According to Moore's law in 1965, Moore's law, someone called Moore's, he noticed that scaling down will continue, and we will continue. What do you mean by scaling down, by the way? Nobody asked me, or all of you know. Scaling down means reducing the dimensions of the MOSFET. As we will see now, reducing the dimensions of the MOSFET. As we reduce it more and more and more, we can integrate more and more MOSFETs on the same integrated circuit chip. So Moore's expected that roughly the number of MOSFETs, the number of transistors on a chip will be doubled every year. And this happened until today, or maybe tomorrow, or maybe 3, 4, 5 years from now. This is the case. But later on, this will not be the case, as we will see very soon.
Since,
Have you thought that?
wasn't it 2 years and then it was reduced to 18 months?
Yeah, it's okay. I said roughly. I didn't say exactly, just roughly. We don't want to argue about this because it is also not 18 months, not 2 years, not 1 year. It is roughly every 1 year it will be doubled. Roughly it will be doubled every year. Of course, this is what the advantage of the scaling down, and this is also a very important observation. Without scaling down, doing the job of a single PC microprocessor chip operating a billion transistor at 2 gigahertz, which is very commonly wide available today, using the 1970 CMOS technology would require the power output of an electrical power generation plant. Now this microprocessor is working from a battery this size. Thanks, alhamdulillah, to the scaling down of the transistors. Without scaling down to the transistor, we cannot achieve this. We would have to use the power of an electrical power plant to supply our microprocessor. Right. Now let us go to what is the MOSFET. I am sure, that most of you know what is this, but just to make things clear, this is the MOSFET. Very simple structure: source, drain, substrate. It has a width and it has a length, and there is a gate, and there is an oxide here. And as you know, we have to apply a voltage, a proper voltage to the gate, between the gate and substrate, in order to establish a channel here. And once a channel is established, we can apply a voltage to the drain, between the drain and the source, and attract the electrons which will be in the channel and generate a current. This is the MOSFET, nothing else. But there are two very important parameters in this structure: the L, the length of the channel, and its width, the width of the channel, the length of the channel and the width of the channel. And of course, the thickness of the oxide, As you probably know, the relationship between the drain current and the gate to source voltage in the saturation region is this one: K equal to VG H minus E threshold squared. But K itself is a constant which depends on the oxide capacitance. The oxide capacitance depends, of course, on the oxide thickness. Epsilon A على T, As we make the oxide thickness thinner, notice this: as we make the oxide thinner, we will get larger C oxide. And as C oxide is larger, K will be larger, and the current will be larger. And getting a high current is always good for us, because this means that we can operate our transistors at higher speed. In the meantime, also, K is proportional to W over L. So the smaller the L, the larger will be K. And the larger will be K, the larger will be the current. Again, we are, or the people in the industry are fighting to reduce the thickness of the oxide, and reduce the length of the channel, and reducing the length of the channel. And the whole story was around this: how to reduce the thickness of the oxide and the length of the channel without, of course, being hurted by the consequences. Because reducing the thickness of the oxide automatically means that the electric field in this area will be very high, and eventually the oxide may be broken down. And reducing the length of the channel means that, we will come to this later on, means that the formation of the channel will not be under the full control of the gate. It may be also affected by the drain, and it is also always necessary to avoid this. We want our channel to be under the control of the gate, only the gate. Otherwise, all these equations will be wrong. Because as you see in this equation, there is no VDS. VDS doesn't appear here. In saturation region, by the way. In other regions, VDS may appear. But in saturation region, we need this equation, and this equation doesn't contain VDS. So we want the control of the channel to be only done by the gate. Remember this. When it started at the first time, in the early 60s, the length of the channel was 10 micrometer. Today, it is common practice to have 40 nanometer. It is quite normal to have 40 nanometer. You can see it's a big difference. And the essential physics, the physics which led to the equation which I mentioned before, remained almost the same. No change in the physics. As you know, we apply a voltage at the gate. This will attract right voltage at the gate. Of course, this will attract the minority electrons in the substrate. This will be brought to the surface of the substrate, but they cannot proceed because there is an insulator. You are imagining what I'm saying? And a channel will be established. Then the relationship between the current in the channel and the voltage between the gate and the source is the square law which I have mentioned. This square law remains the same over the years. For about maybe 50 years now, this square law characteristic remains the same because the structure remains the same. But of course, things are coming to change. Problems of scaling down, as I mentioned, the electric field inside the oxide will be very large, and eventually the oxide is very thin and may be broken down. Heating up the transistors, if they are scaled down and they are placed together, very close to each other, in just a chip of much lower than this area, they may be heated. And this heating may affect neighboring transistors, and as such, the operation of the integrated circuit may not be reliable. These are the disadvantages of scaling down, and of course, as I said, the classical physics which led to this square law equation doesn't work anymore. Why? Because when the distances are too small, electrons may start to change their mind. Rather than waiting until the voltage attracts them and move smoothly, as we know, they may start to think in a different way. They may start to do tunneling. tunneling يعني ايه؟ يعني نط. يعني بدل ما الالكترونات تمشي كده بهدوء عادي فولتج بيشدها وهي تنشد لورا وتمشي تبتدي الالكترونات تنط. ازاي تنط؟ This is a simple explanation for this phenomenon. The electrons today are not considered as particles as we used to do long ago. They are considered as waves. A wave with certain energy. If a wave with certain energy faced an insulator, this is an insulator, the wave will not stop. It will continue. It will cross the insulator and appear at the other side with lower energy, yes, but it will appear at the other side. This phenomenon we call it tunneling. And it will take place, of course, if the width of the insulator is too small. Because electrons will not wait until we apply the high voltage and attract them. They may take other decision. They may start tunneling across the insulators. And as such, they may produce leakage currents. So rather than electrons come to the surface of the substrate and stop there because there is a thin insulator or silicon dioxide which prevents them from proceeding, they can jump. And they can tunnel. And as such, there will be a gate current. And the major advantage of the MOSFET, which is having zero gate current, will be lost. You know this. The major advantage of the MOSFET is having a zero, almost zero gate current. This will be lost. Now the leakage current will be large. Remember this expression, the leakage current. The leakage current, the current which will proceed from the substrate to the gate and make the gate current not almost equal to zero. And this is a great advantage which we want to preserve. We want to keep the gate current equal to almost zero so that we can get high impedance and so on. So this is the phenomenon of tunneling. Scaling techniques. How the scientists start to go around these problems? Remember that we want to reduce the length of the channel. We want to reduce the thickness of the oxides. Huh? But there are problems coming from this. But the end result is we want to increase the current. Increasing the current is always good because this means that we can have faster device. How the scientists got around this? They added, first thing, they added nitrogen to the silicon dioxide. The silicon dioxide, if we add nitrogen to it, this will reduce the leakage current. Now, we are not going to go in the details of how this will happen. I'm just summarizing what happened, rather than explaining how exactly it happened. Because this will get us a lot of physics and chemistry. We are not prepared for this now. So adding nitrogen to the silicon dioxide of the insulator will reduce the leakage current maybe by 10 times. This was the first idea which came to their mind. The second thing, rather than using the silicon dioxide as an insulator, use other dioxides as insulator. And of these dioxides, zirconium oxide, aluminum oxide, hafnium oxide, and so on. And it was found that using these insulators rather than the silicon insulator has increased the dielectric constant by maybe 6 times. And as such, we can obtain same value of oxide with higher thicknesses. You understand what I mean?
Yes.
Please, feel free to ask any question anytime. The most important thing is you understand what I'm saying. Also, we always say that the MOSFET is a metal oxide semiconductor. This was the case when it was invented in the first time. The gate, because metal stands for the gate, oxide stands for the oxide, and semiconductor stands for the substrate. When it was invented, yes, the gate was made from metal, aluminum, say. But then they changed their mind and started to use polysilicon, which is an almost conductor. It is silicon, but almost a conductor. Polysilicon as a conductor instead of the gate. And as such, most of the MOSFETs which were used until 2008 was not built using metal for the gate. Were built using polysilicon for the gate, which is an almost conductor. But then they changed their mind, and from 2008 until now, they came back to using the aluminum for the gate, or the metal for the gate. But using this have improved the performance of the MOSFETs. Another way of thinking is the following. If we want to keep the channel under the control of the gate, so why not use one gate only as a structure which I have mentioned? Now, the structure I mentioned so far, we are using one gate only. So why not to surround the channel by gates from every side? يعني تبقى الchannel في النص وجيت من هنا وجيت من هنا وجيت من هنا وجيت من هنا. 4 gates rather than one channel. And in this case, the gate will be always, in this case, the channel will be always under the control of the gate, because from any direction there is a gate. Before, there is a gate only on the surface, but far away in the bottom of the substrate there is no gate. So the drain is doing whatever it wants to do. You understand me? Yes. But with the gate surrounding the channel, now wherever you go in the channel, there is a gate very close to it, and the channel will be under the control of the gate. And as such, we can avoid the leakage current which may go under the table. يعني اللي هو أنا شايف اللي هو يعني leakage current اللي هو ممكن يروح من السورس للدرين, not under the control of the gate, now will disappear, will vanish, because the channel will be always under the control of the gate. So the current which may go from the source to the drain without the control of the gate will almost vanish.
So where would be the drain and the source position now? Because there isn't any, the channel is not surrounded by the gate.
No.
How is the drain and the source?
The drain will be here, the gate will be here, and the gate will be surrounded around.
Now the units of the substrate will be at the bottom?
Yes, at the bottom. Yes.
Yeah, but how about the drain and the source? Usually they are on the sides.
No, this is usually.
Yeah.
But now they're changing their mind.
Yeah.
Rather than having the drain and the source as the classical way explains, now the drain and the source will be in different locations.
Yeah,
But the most important thing is that the gate will be surrounding them. Not necessarily totally surrounding, but at least we will have 4 gates.
Yeah.
One gate from here, one gate from here, one gate from here, one gate from here. Wherever you are in the channel, you will be under the control of a gate, of the 4 gates. وسموا ده فين فت، أنا شايف سموا ده فين فت، والفين هنا بمعنى زعنفة، يعني كأنها على شكل زعنفة السمكة يعني، زعانف السمكة، كأنها على شكل زعانف السمكة يعني، صح؟ فين فت، سموا ده فين فت. اتفضل.
Doctor, we're doing this to get from power consumption, standby.
No. We are not doing this to get rid of power consumption. We are doing this to get rid of the leakage current which may flow from the source to the drain under no control of the gate. And if there is such a current which is flowing under no control of the gate, then our formulas are wrong. Because our formula is our formula is based on the fact that the current is established only when a voltage is applied between the drain and the source, and the channel is formed under the full control of the gate. And as such, it is K VGS minus V threshold square. But now, if there will be a current between the drain and the source under no control of the gate, then this formula will be wrong. And all our designs will be wrong. So the idea was to keep the channel still under the full control of the gate, despite the very small length of the channel. Because as the length of the channel is decreased, the drain now is seeing the source. You understand what I mean? They are very close to each other, so current may jump from the source to the drain without the control of the gate. In order to keep the control of the gate in place, they decided to use many gates. Many gates. زي زعانف السمكة كده. هنسموها FinFET. I will.
But wouldn't that increase the parasitic capacitance value?
Yes, it may. It may increase. Of course, there are always pros and cons for any solution. But this was a solution, طبعا. It has pros and it has cons. It may increase the parasitic capacitance. I agree with you. But this is the case. Yani we have to, if we gain something, we have to pay the price somewhere else. You agree? This was a possible solution for the leakage between the source and the drain, resulting from the very close or very short distance between the drain and the source. Notice that the drain can see the source directly, and it doesn't need anything from the gate. So the channel, there will be a leakage current under the gate, without the control of the gate. You understand what I mean? And as such, all our formulas will be useless, and we cannot live this way. This is what they call the FinFET. As you can see, gate from up, gate from down, maybe we get from this side and we get from the other side, and the silicon is in between. So the channel is in between, and it is under total control of the gate. These are the trials and the efforts done by scientists in order to improve the performance of the MOSFET while reducing its dimensions, while reducing the thickness of the oxide and reducing the length of the channel. المعركة كانت هي دي. How to reduce the thickness of the oxide and the length of the channel while keeping everything under control. But it appears that there is no way to continue in this direction. According to the semiconductor industrialists, they expect that by 2020, but it is not of course a fixed time. It is around 2020. There is no way to reduce the features of the MOSFET anymore. We cannot go anymore because we cannot add anything new. We cannot. The tunneling will start to appear, and the leakage will start to be more excessive. And even more than that, the models we are using, the models we are using to model our circuits will be useless. All the SPICE models available are not taking into consideration the leakage current and the tunneling of the electrons and all of this. So we will be in trouble.
Does that mean electronics will die eventually?
We are here to prove that it will never die. As long as we are alive, it will never die. Because as long as we are alive and need electronics for essential things in our homes, and even for entertainment, electronics will never die. If the electronic die, there will be no mobile phones. There will be no radio receivers. There will be no TV receivers. There will be no microprocessors, no microcomputers. If the electronics die, then this means that the world as we know it today will go.
But there is a point where you cannot improve anymore. For example...
Now this is why we are here as well. To show that, yes, no way to improve anymore on the scaling down of the MOSFET. Then we have to find other ways.
That means we'll have another technology.
Of course. Well, why I'm here? To introduce you to this new technology.
Okay.
All what I have said so far is a little bit of history. How it was developed, what the problems we are facing, and to prove that we cannot do anything more. So we have to change our mind. We have to change our direction. We have to move in another direction, or in other words, we have to find a new technology. So, And this is the heart of the lecture, of course, or the seminar, in fact. It's a new technology. ماشي؟ Any more questions so far? طب ما تشوف كورس خد على وقتك. أنا مش عايز طبعا. تعال. أنا أكيد مش عايز. We agreed? The scientists have done their best to scale down the transistor, the MOSFET, as much as they can. But they are facing the physical problems. No more scaling down can be done while maintaining the relationships which we know as is. No way. So we have to think in a different way. And this is what is coming soon, inshallah. The carbon nanotubes, the single electron transistors, and the membristors. And we will start with the carbon nanotube. It is the most developed one of them, and it is around us anyway. In a way or another, it's around us, but not, of course, very popular as the MOSFET which we know. The carbon nanotube is based on the idea, and of course, if you go to the people in the chemistry department, they will say, what's new? We know the carbon nanotube since 30 years ago, and they are right. But they don't know it as an electronic device. They don't know it as an amplifier. They don't know it as an oscillator. They know it as a chemical development. But here we are discussing it as an electronic device, which can work as an amplifier, which can work as an oscillator, which can work as a digital gate, digital logic gate. So the carbon nanotube we are talking about may be the same as the one in the chemistry department, but we are talking about it as an electronic device, which can be used for building electronic circuits. You understand what I mean? So it is not new. It definitely is not new. It is not since 30 years ago, but from the chemical point of view, not for us as an electronic device. The carbon nanotube is based on the idea that the material, any material, it behaves in two totally different ways when it is large scale or small scale. For example, the carbon, we know its properties as a larger scale carbon, but in nanoscale, it behaves in a totally different way. Some elements, they are in larger scale, they are insulators. When we go to the nanoscale, when I say nano, I mean dimensions in terms of nanometer. يعني 10 to the power minus 9 of the meter. يعني something very, very small. يعني maybe the diameter of the hair is around 100 nanometer. Do you understand what I mean? Yeah. So, what I was saying. So the material behave in the nanoscale totally different from their behavior in the larger scale. So the carbon which we know, it is around us of course, will behave totally different in the nanoscale. It will behave as a semiconductor or even as a super metal, a metal of very high conductivity, much better than any metal we know. And it may behave as a semiconductor as well, much better than any semiconductor we know. But this depends on how you develop the carbon nanotube. And we are not going to discuss the details of this. This is physics and chemistry. We are not going to discuss it. But anyway, we assume that we have a well-developed carbon nanotube. It can behave as a semiconductor material. It can behave as a metal. And this was very attractive to scientists because this said that this means that we can build an integrated circuit without using any copper wires. Now, believe me, the bottleneck in designing high-speed computers is not the physical characteristics of the transistors. It is the characteristic of the interconnects. الأسلاك يعني اللي بتوصل الترانزستورز مع بعضها on the chip. It is the characteristic of these interconnects which decide today the maximum speed we can achieve using computers. It is not the physical features of the devices, no, or the transistors, no. It is the characteristics of interconnects. Because these interconnects at very high frequencies, they have transmission lines, and these transmission lines have very complicated characteristics. I'm not going to discuss it here, of course, but it has a complicated characteristic which must be taken into consideration by a digital circuit designer. And fortunately, or maybe unfortunately, This is an analog technique. That dealing with the transmission lines is an analog technique. And this is a proof that the people who are thinking in one direction only, analog or digital, they are totally wrong. There is nothing today called analog or digital. Everything is coming together to build one system, analog and digital. Right? Once this carbon nanotube can be used as a semiconductor, it can build the amplifiers and the transistors we want, and it can be used as a metal as well, it can build the interconnects. And as such, we can have one element only on our chip. And this, of course, will make life much easier for the manufacturers and for the scientists. This is how the carbon nanotube looks, but don't forget the diameter of this carbon nanotube is 1.5 nanometer. يعني دي مكبرة كام مليون مرة. مش كده؟ It is just 1.5 nanometer. This is how it looks. And depending on the angle of development of this carbon nanotube, it can work as a very good metallic conductor or a very good semiconductor material. The electrical conductivity of metallic nanotube can exceed that of the best metals. The transconductance and mobility of nanotube can exceed that of the best semiconductor. So it is better in all cases. Nanotube's environment may affect whether it's truly metallic or not, and it's not necessarily. Nanotube diodes are available, nanotubes amplifiers are available, and this is how MOSFET, how a carbon nanotube FET can be developed. What was the problem with the MOSFET? The thickness of the oxide, it cannot be reduced below few nanometers, and the length of the channel. Now, by placing a carbon nanotube between the metallic source and the metallic drain, the drain and the source are now metallic. They are not anymore semiconductors. Between the metallic source and the metallic drain, we add here a carbon nanotube. This is our channel. This will be our channel. And the silicon dioxide will be here. We don't care much about its thickness, and the gate will be here. And under the effect of the gate, we can control the amount of current which will flow between the source and the drain without being so worried about the thickness of the channel. The carbon nanotube is there. There are, of course, voltage, current characteristics, and so on. Everything available for the MOSFET is available also for the carbon nanotube, but I don't want to go to these details. So what happens, they replace the channel by a carbon nanotube. So this is a carbon nanotube. And now all the problems of having a thin oxide and all of this does not exist. Because it is just a carbon nanotube and it is working under the effect of the gate. And the thickness of the carbon nanotube is now as low as 1.5 nanometer. Carbon nanotube find applications in analog as well as in digital, but the very important thing here is some scientists have designed and fabricated a full AM receiver using carbon nanotubes. But this full AM receiver contained resonant antenna, fixed RF amplifier, RF mixers, and AF amplifiers. But the point here is that this was developed by people from different departments, from physics, from materials, from material science and engineering, from electrical and computer engineering, and from chemistry. So it needs a group research. It cannot be done by an electrical engineer only. It needs a group research to do it. Because it is something very complicated and it cannot be done by a single person or even two.
What's so special about the nanotube that it won't have any leakage current later on?
Naturally, because now the carbon nanotube is connected directly between the source and the drain. You agree with me?
Yes.
And between the source and the drain, there is an insulator here. This is insulator. So the current wouldn't go this way. It cannot go this way. This is an insulator. There is no current here. So as such, we are the only connection between the drain and the source is the carbon nanotube. we don't worry much about any leakage current because the drain is seeing the source via substrate. We don't care about this. You agree with me? Carbon nanotubes also are available now for digital circuits, and there are so many different digital circuits which are available. The sensors, they are applied in half. They are applied also in designing sensors. And also there are trials to combine CMOS technology with carbon nanotube technology. But the problem in this is temperatures of operation required. The carbon nanotube, in order to develop it, needs a higher working temperature than what the silicon can sustain. But even though people in some institutions manage to build an inverting operation amplifier circuit like this, with this resistance alone made of carbon nanotube. The point here is they managed to combine carbon nanotube technology with silicon technology, which is used to build the operation amplifier. So this proves that the carbon nanotube technology can be compatible even with the CMOS technology, which is available today. But what people are expecting is that the carbon nanotube technology will totally replace the CMOS technology. So that
I've read somewhere that the maximum frequency in nanoelectronics is about 100 gigahertz.
well, if this is the case, we will be very happy. 100 gigahertz is not a small frequency.
Yeah, I mean, does this technology, the nano carbon tube,
Of course, it is quite easy because now we are talking with very small dimensions.
does it exceed the 100 gigahertz?
It can exceed, of course, but 100 gigahertz itself is not bad. It's very good. It's very, very high frequency. The second device which I want to introduce to you is the single electron transistor. And can you imagine this? A single electron transistor. A transistor working with only one single electron. Or its operation is based on the motion of electron by electron. You can immediately comment that the current will be so small. I agree with this, but still the idea is very interesting. How it works? Imagine that we have an island here, and this island is surrounded by an insulator, and we apply the voltage between the terminals of the insulator. Practically, we don't expect any current. But if we consider back again the tunnel, then the electrons which will reach here can tunnel and cross this insulator and reach to the other side. Subject to the condition that this width is very small. Like if we take into consideration the fact that the electrons are not anymore particles but waves, then the electron can jump from this side to this side via the phenomenon of tunneling which I explained before. The idea of the single electron transistor is based basically on this very fact. And let us see how it works. This is a comparison between the MOSFET, which we know with gate, with gate, channel, drain, and source, and this substrate. This is the MOSFET which we know. And this is the single electron transistor. We have a gate, but not the same as this gate. We have a drain, but not the same as this drain. And we have a source, but not the same as this source. And we have a conductive island, which is something equivalent or similar to the channel. But don't forget that they are all isolated from each other. How it works? This conductive island can accommodate one electron only at a time. Remember this. It is so small that حتى بيسموها ساعات quantum dot نقطة يعني. It is so small that it can accommodate only one electron at a time. Under the effect of the gate, one electron will move from here to the quantum dot, or this island. And it will stay there until the right drain voltage is applied. So it will attract it from here to the drain again. Then, it is ready for another electron to jump from the source to the conductive ion. And it will be ready to be attracted by the drain to the drain. And as such, we are getting current. But the current is moving one transistor at a time. This is why single electron transistor. It has very interesting characteristic. No time to, or no space to explain it here. It's complicated. But it is a transistor. And it has been used as an amplifier and as a logic gate and has so many applications for single electron transistor. But the point is, the carbon nanotube, the single electron transistor, and what is coming, all of these are still in the research laboratories. They are not available commercially yet. But maybe, maybe by 2020 or 2015 or 2016, they will start to be commercially available. There are many research laboratories around the world who are working very hard. طبعا كلهم عايزين يكسبوا السباق عشان هم اللي يعملوها الاول ويجيبوا فلوس كتير. They are fighting in order to reach the level of commercialization first. Because the one who will reach the level of commercialization first will gain a huge amount of money. حد عايز يسأل حاجة؟ Please feel free to ask any question. Applications and fabrication of the single electron transistor. The single electron transistor is more compatible to silicon technology rather than the carbon nanotube. Obviously, carbon nanotube carbon. But the single electron transistor is silicon. It is very compatible to the silicon technology. And as I said, there are so many applications for the single electron transistor, like the carbon nanotube. It can be reduced as an analog circuits and digital circuits and so on. ما تنامش عشان انا ما انامش كمان. ما تنامش كده، انا كده. اصحى معايا، خليك صاحي معايا. Now the third element, which is the mem resistor. The mem resistor. And the mem resistor stands for memory resistor. We know that the capacitor is a memory element. We know that the inductor is a memory element. But we never heard about the resistor as a memory element. And it remembers what? It remembers the magnitude of the current, the last current which passed through it. And its value will depend on this last current. Can you imagine this? يعني in order to explain it more, imagine that we have a pipe. ماشية فيها مية، صح؟ And this pipe, it changes its diameter according to the speed of the water. And by the end of the process, when no water is coming, the diameter of the pipe will remain at its last value. Can you imagine this? This is the resistor. طبعا in electrical engineering مش مية وبايبس.
But will the diameter increase as the current increase or decrease?
Increase. The diameter increase as the current increase. يبقى the diameter is keeping changing as the current is changing. ادي اول واحده. طبعا احنا مش ماشي حاجه كده قبل كده، البايبس ما بيتغيرش الدايمتر بتاعها. ادي اول واحده. ثاني واحده ان the last diameter of the pipe will be decided by the last amount of current which passed. اتفضل.
So, in DC or AC, we don't stop the flow of current generators in circuits. So, how do what's the
We stop. If I have a circuit with one resistor and one supply voltage and a switch, if I put the switch on, the current will flow. If I put the switch off, I stop the current. So the point is that the value of the resistance is not constant. It depends on the amount of current which is flowing to it. So if I keep changing the DC supply, the current will keep changing. And the value of the resistance will keep changing. And the last value of the resistance will be dependent on the last value of the current. Something strange, it is not something usual, it is totally unusual. This memristor was suggested by Leon Schwab in California, Berkeley, in the 1970s. He expected زي كده الجدول الدوري بتاع المدارية لما اكتشفوا مواد كثيرة جدا لمجرد ان الجدول الدوري بيقول ان لازم يكون في الحته دي هنا ماده تسد الفراغ. I'm sure you are aware about this. صح؟ بنفس الطريقه دي ليون شوا اكتشف ان لازم يكون في fourth element. بالاضافه الى الاندكتور والكاباستور والريزستور اللي احنا عارفينهم لازم يكون في فورس اليمنت. واكتشف العمليه دي ازاي؟ طبعا ده مش رسمي يعني لكن انا نقلته لكنه مفيد ان شاء الله. اكتشفوا كالاتي، قال ان احنا عندنا 4 electrical variables: current، الفولتج، التشارج، والفلكس. 4 electrical variables. وعندنا ايه؟ ريزستور وكاباستور واندكتور. والعلاقات بينهم 3. العلاقه بين الريزستور هي علاقه بين الفولتج والكرنت، دي في باي دي اي بيساوي اي. والعلاقه بين الفولتج والتشارج هي بتاعت الكاباستور، دي كيو باي دي في بيساوي سي. والعلاقه بين الكرنت والفلكس هي بتاعت الاندكتور، ال بتساوي دي فاي باي دي اي. اذا لازم يكون في عنصر رابع، لازم يكون في فورس اليمنت بيربط بينه مين ومين؟
فلكس.
بين التشارج والفلكس. وقال لازم العنصر الرابع ده تكون العلاقه بتاعته دي فاي باي دي كيو تساوي ام. ام طبعا مش نيوتن اندكتنس، ام هنا ممبريستور. فليون شوا في السبعينات في كاليفورنيا قال لازم يكون في عنصر رابع. لكن it took about 40 years until people in Bell Labs managed to fabricate this force element, which is and it is now available. I think in 2008 it was developed for the first time. For the first time the memristor was developed. It is a new element, as I explained. It has a memory, and the relationship between the flux and the charge across it is this new term which we call M. There are of course nano devices. They can be fabricated on the nano scale, nanometers only. So they are member of the families of nano devices. Where the membristors will take us, there is a big debate. If you go to the internet and the Google, you will find a big debate about the membristors. Are they going to change our life totally? Some people say yes, some others say no, and I will go in between. I will say they will definitely change our life, but not totally. They will definitely change our life because these are new devices, our new circuit element. Using it, we can have new devices, new technologies, and new changes in our life. So definitely they will change our life, but not totally as some very optimistic people say, and not also not going to do any effect like some pessimistic people say. Life is always somewhere in between. So definitely they will change our life. As I said, they are available. There are few ground bit arrays now using this memristor, and they can be fabricated using metal and titanium dioxide, so they are not compatible with the silicon anymore. So the only invention which is compatible with silicon is a single electron transistor. The carbon nanotube and the memristors are not compatible. This is maybe useful for you. The circuit modeling of nano devices. All the SPICE models which are available today cannot be used for circuit modeling of nano devices. This is all again in the industry. There are so many ideas in order to invent new softwares which are compatible with the new nano devices, taking into consideration their structure, and even which take into consideration the problems of the MOSFET, including the leakage current and so on. There is no need to go into the details, and of course taking the quantum effects into consideration. So in conclusion, nano electronic devices are here to stay. Carbon nanotubes are here to stay. Single electron transistors are here to stay. Memristors are here to stay. Which one of them will be influencing our life more? Allah only knows. محدش يعرف. بس ربنا يعرف. مين فيهم دول اللي هيأثر في حياتنا أكثر؟ محدش يعرف. دي يعني في علم الغيب لسه. لكن بالتأكيد هذه العناصر ستؤثر في حياتنا. Because we are living and witnessing the third revolution in electronics أو in electronics. تمام؟ طيب جزاكم الله خير. I am done.
commercially?
Are we?
Commercially or?
No. None of these devices is available commercially. They are still in the research laboratories. But in the research laboratories, they are producing almost everything. Radio receivers, digital logic gates, filter gate arrays, anything you can imagine, but in the research laboratories. In order to be available commercially, it needs still more time to make them compatible with the commercial life.
Is it possible in the coming few years that we see the memristor as a discrete element?
I don't think so. This is a nano device, and it is not designed to be just a discrete element. It is designed to build billions and billions of transistors on the same chip. So I don't expect that it will be available as a discrete element. People are after it in order to integrate, in order to have billions and billions of transistors on the same chip, in order to make all the mobile sets now, or the mobile devices, available. Otherwise, they are not. So I don't think so, that they will be available in discrete form.
So does the invention or discovery of the
Memristor.
add a new field to electrical engineering in general? Because
Of course.
capacitors not
Of
only-
course, I think that by time we have to change our circuits course. Because in our circuits course, we teach students that there are only 3 elements. In fact, there are 4. And this 4th one is coming soon to affect our life. I think also that we have to change our electronic courses, because we are focusing on MOSFET and the bipolar junction transistors, and eventually, in 5 years or so, maybe 9 years, something like that, this will go. And there will be new devices available around us. So definitely this will affect not only our life outside the university, it will affect our life inside the university in terms of the curriculum we are teaching the students. We have to take this into consideration. And if the electronics will change and the circuits will change, then everything in the electrical engineering and the computer engineering, of course, will change.
You mentioned that we will today combining the techniques of digital analysis and analog analysis and overall circuits.
Of course.
But we also
Not only today, this was long ago, but there was always a common understanding among some people that digital is a different word, totally different word from the analog. And we have to be either digital or analog. This is totally false and wrong. It was never like this before, and it will never be in the future. Except, of course, if we consider the period of time when there was no digital techniques at all. Yani 50 or 60 years ago, the television was totally analog. Today it is mixed. It is mixed between analog and digital. So we can imagine a world which is totally analog. This is imaginable because we are analog. And everything around us, serving us, must be analog. We can imagine a world which is totally analog. We cannot imagine a world which is totally digital. But today, the common practice is a world which is mixed, analog and digital.
how can we classify these new ideas?
My ideas?
No, these new.
These ideas, it works on both sides. As I said, there are single electron transistor based analog circuits, amplifiers, and single electron transistor based digital circuits, digital logic gates. Both of them are available. And every scientist now, when he invents a new device, he keeps this in mind. He has to invent something which is compatible with both, which can work with both, not only on one side. Can you confuse all
Some professors say that there will be a day that technology will use light instead of electrons, because light is much faster and lighter.
Maybe.
And
Maybe.
what's your
This is,
comment?
I wouldn't say there will be a day so strict like this. Because everything in our life had advantages and disadvantages. There are always advantages for using light as a carrier for the information. There is always advantages for using electrons as a carrier for the information. So it is hard to say that anything will disappear. By the way, do you think that the vacuum tubes are not existing today?
Yeah?
No, this is totally wrong. This is totally wrong. Even the vacuum tubes, which was invented more than 100 years ago, are still available today. And even in some areas, I will tell you, don't worry. And even in some areas, they are coming back. Where they are available today, not necessarily but خلينا نتكلم بالجنرال. In clystrods, in traveling wave tubes, which is widely used in satellites, in magnetrons, in tetrodes, which are very high power amplifiers used in transmitter stations, in cathode ray tubes. Most, I would say 80% of the TVs still used by us are based on the old technology, which uses cathode ray tubes. The cathode ray tube is a vacuum tube. So the vacuum tubes are still there, and I will tell you more. They are coming back, because it was discovered after this long years of experimenting with the transistors that the best sound you can hear is a sound produced by a vacuum tube. Really? Believe me. Believe me. Believe me. You go to the internet, go to Google, and ask for glass sound. They call it glass sound, or glass audio, or glass audio. That is to say, the sound which is produced by the vacuum tubes, because they are glass. And you will discover that many people in the area of sound and sound effects and so on, and sound reproduction, they prefer vacuum tubes over the transistors and the bipolar junction transistors. Because of the noise, yes, because of the noise. Because the vacuum tube, although it needs heating in order to work, but it is still less noisy than the transistors, so whether it is bipolar or MOSFET. I am just mentioning this to tell you that there is nothing which will die totally. Because even the vacuum tubes, although it is not very widely used, and I am sure maybe 99% of you were not aware about it before they are coming here, it is still alive and it's still around us, but in very limited applications. I must add that.
At the end, we would like to thank Dr. Abu-Almaati for honoring us and sharing this information with us. And we would like to thank you also for coming. We hope you benefit and you share our new ideas about our Thank you very much.